In this video, I'm going to walk you through some calculations with uncertainties. I think this is a really important video, and I would take your time with it. These are calculations that sometimes even like the grade 12 students make mistakes on. I think you should maybe pause after each section and come up with your own questions to really help reinforce it. So there's three parts. I'm going to show you first just how to add or subtract measurements with uncertainties. So here's an example. Let's say you start with 20.5 milliliters, and after perhaps a titration or something, you have 15.45 milliliters. You want to know how much was the volume that was released. Well, the simple math of 20.5 minus 15.45 is not too tricky. So let's just maybe go through the answer here, and then we'll work backwards, and we'll show you why that's the case. The main thing to remember is when you're adding or subtracting, you need to add the uncertainties together. So the difference in the volumes is 5.05 milliliters. And if we add the uncertainties together, we get 0.10 milliliters. Okay, now let's just think about why that is. What we're saying here in the top one is this could be as high as 20.55 or as low as 20.45. Okay, similarly with the final volume. So let's just take the highest possible initial volume of 20.55 and let's subtract the lowest possible final volume, which would be 15.40. And you'll see that we get 5.15 milliliters. And also, if we take the lowest possible initial volume, 20.45, and subtract the highest possible final volume of 15.50, we get 4.95 milliliters. Okay, so it's anywhere between 4.95 and 5.15 is possible. So hopefully you can see why this is the correct way to do it. That's exactly what our answer says. This is as low as 4.95 or as high as 5.15 milliliters. So maybe just pause that and think through that, come up with your own numbers, and do another practice question. Often in our labs we'll do multiple trials, and then we'll need to calculate the average. So let's say this is a titration in chemistry, and you're measuring out 3 volumes, or you're doing 3 different trials of the same thing, and you need to calculate the average. Well, at this point, hopefully everybody knows how to calculate the average. If you add those 3 volumes up and divide by 3, you're going to get your calculator will tell you it's 17.423 continued a whole bunch of times. Now at this point, these uncertainties here, which you would still record in your raw data because they show the uncertainty of the instrument you used, but at this point they become more or less irrelevant because the difference between the 3 trials we did exceeds the measurement uncertainty for each trial. So the way to calculate the uncertainty for this average is to look at which of these 3 values is furthest away from the average, or the mean that we just calculated. And it looks like this one is the furthest away from 17.423. Okay, so we can just do a quick subtraction to see what the difference is between those two, and we get 0.12 as the difference. Okay, so our answer should be, at least initially, 17.423, that's the average, plus or minus 0.12 milliliters. So this is called the range. This right here should be high enough that it encompasses all of the values we got in our trials. Okay, now it's possible that one of these trials is an outlier and we would omit it, and that's kind of another story. Let's just assume for this example that all three of these are valid results. There's no outliers here. Okay, we're almost done. The IB program says that you can get away with one significant digit in your uncertainties, which means that we could round this down to 0.1. So if we round that down to 0.1 milliliters, we're going to also round this value here to the same place value that we rounded here. So if we round this down to the tenths, then we're going to round this to the tenths as well. And so our final answer, it's getting a little messy here, our final answer would be 17.4 plus or minus 0.1. And if you think about it, that means we're saying that the average is as low as 17.3. Okay, well that kind of makes sense. And as high as 17.5, which is pretty close to the maximum value we got. That's good enough. So that's how you find the average with the uncertainty. When the uncertainty is represented as a range. There's other things you can do here, like use the standard deviation instead of the range, but I'm not going to worry about that right now. And the last part here, and this is probably one of the more challenging parts for students, is what do you do if you're multiplying or dividing measurements and those measurements have uncertainties with them? So the steps, and we'll do an example in a second, is the uncertainties need to be changed to a percentage, and then you're going to do your calculation. Then you're going to add those percentages together, and then you're going to change them back to absolute uncertainty, which is just like normal uncertainty. Like this is absolute uncertainty. So this is a density question. We've got the volume of an unknown liquid, and we've got the mass of that liquid, and we need to find the density. Okay, and I think most people would know that density is mass over volume. Now, everybody can divide 11.75 grams by 14.04 milliliters, and we can calculate our density. It's going to be something like 0.788818 grams per milliliter. Okay, but how are we going to deal with the uncertainties? I'm just going to rewrite the density here. Have a little more space here. So that's what we recorded as the density. For the uncertainties, we're going to change them to percentages and add them together. So for the volume, we want to know what is 0.1 milliliters as a percentage of 14.04. So we can work that out. Oops, 14.04 and multiply by 100%, and we get, it's going to be a very small number, 0.71225071. I'm not doing any rounding yet. I'll round at the very end. Okay, so that's the volume uncertainty as a percentage. Now we're going to look at the mass uncertainty as a percentage. 0.001 as a percentage of 11.075. This is going to be a little smaller, 0.0090293.5%. Okay. Now I'm going to add these two together. Add those two together, and we get 0.72128,006%. Really don't need all these digits. That might make things a little more confusing, but hopefully you can still follow along with what I'm doing here. So we're almost there. Let's just kind of rewrite what we have so far. The density is, of this unknown liquid, I'm just going to round a little bit here, 0.788 0.78 grams per milliliter, plus or minus, and the uncertainty here is a percent, 0.721%. Okay, I'm just rounding to make things a little easier. Now we're almost done. We are going to turn this back into absolute uncertainty, which means the same units, grams per milliliter. We're not going to keep it as a percentage. So now we need to figure out what is 0.721% of 0.7888. Okay, so we're going to figure that out in our calculator. So we're going to divide that by 100 and then multiply it by 0.7888. And we're going to end up with that, again, plus or minus 0.00569 grams per milliliter. So it's back into grams per milliliter. Again, the IB program says we don't need all these significant digits in our uncertainty. We can round it to 1 sig fig. So this would become 0.006 grams per milliliter. That is in the thousandth column, which means I can round this to the thousandth column too, 0.789. And this is the way to write your final answer. 0.789 plus or minus 0.006 grams per milliliter, which happens to be the density of ethanol.